Okay, so we start by describing the key things that you need to understand or that you need to know for you to be able to answer any question on RC, RL. After that, we're going to look at some examples from basic to complex, basically on all the ideas that we'll describe. The first thing that you need is that if you have a capacitor in a circuit, the natural response or the response from a capacitor has a formula we can use. We start first by talking about the charge that a capacitor stores, because we know a capacitor is basically a passive element that stores energy in its electric field. Now, the energy, of course, is in terms of charge. So we can describe the charge stored by a capacitor to say to be proportional to the voltage that is used to charge the capacitor. From here, we end up with the expression charge is equals to Q C, the capacitor, times V. When you work with this expression, you can actually end up with a mathematical representation of current, because we know to say that when you differentiate charge with respect to time, you get current. So implying that here you have a current from a capacitor will be equal to the capacitance dV dt. So in a rare situation, you might be required to use this expression. In the same way, if you're dealing with an inductor instead, just like a capacitor, an inductor also stores small amounts of charge, small amounts of energy in its electric field. So an inductor, however, we look at it in terms of voltage. So the voltage across an inductor can be obtained using its inductance and the current passing through it. So what is going to be the formula in this case? So for a capacitor, we saw that it was C dV dt. It was I, which was equals to that. For an inductor, now we have V. So let's swap them. Instead of capacitance, we use inductance. Then this one will be di dt. So this is going to be for an inductor. Now, if you know the current and you have a resistor, this is the current coming from a capacitor, you can easily obtain the voltage from this by integrating the V here. You can easily obtain the power and so on. So these two are the basic ones that you need for a start. Now, when part of a circuit and when a capacitor is the only device, other than the only element, let's say you have a capacitor and a resistor. So in a capacitor and resistor only circuit, the response that you get from a capacitor is actually in terms of the voltage. In the hand, all right? Okay, so in a resistor capacitor circuit, when you only have resistors and a capacitor, no any other source, the response that you get from a capacitor is in terms of the voltage. And we actually call that the natural response. So in this case, the natural response that you get from a capacitor is going to be in terms of voltage, and it will be given by Vt is equal to V0 E minus T over the time constant. For a capacitor, the time constant will be given by the resistance multiplying the capacitance of that capacitor. Here, the resistance, you have to take note that this is the total resistance in the circuit. Meaning, if you have 2, 3, or 4 resistors, you have to combine them into one resistor. Farai, do you have a question? You had your hand up. Okay, so this is if you have only capacitor and multiple resistors in a circuit. If instead of a capacitor, what you have is an inductor and resistors only, so in a resistor inductor circuit, the response that you get from an inductor will be in terms of the current. So in this case, you're going to have I0 e to the minus t over tau. But for an inductor, tau, which is the time constant, will be given by the inductance divided by the equivalent resistance in that circuit. Tau here is the time constant, and the units here are the seconds. Even here, the units are the seconds. V0 is the voltage across the inductor at t is equals to 0, or for t less than 0. In the same way, I0 is the current through the inductor. This is the voltage across the capacitor for t less than 0. This is the current through the inductor for t less than 0. We'll look at a few examples to just make sure you understand how to find these and how to use these equations. Before we get there, do we have any questions? Okay, looks like there are no questions. Consider a question like this one. For this question, they're saying, assuming that the switch in the figure has been in position A, so position A, it has been like this for a long time, and it is moved to position B at t is equals to 0. Then at t is equals to 1 second, the switch moves from B to C. Find VCT for t greater than or equal to 0. So we're looking for VC. And what we're dealing with, this is a capacitor. So for a capacitor, we recall that the natural response from a capacitor, Vt, is equal to the voltage initially for t less than 0, multiplying e to the minus t over the time constant. And for a capacitor, T is equal to RC. So the first thing that you try to get here, the first thing that you get is V0, the voltage for T less than 0. So you redraw the circuit and look at it for T less than 0. Here we'll not redraw, we'll just shade out what we do not need. So if we're going for t less than 0, what are we going to be seeing? So firstly, for t less than 0, we know the switch is at position A, implying that this is not there. It's not doing anything in our circuit. So is this line. It's not doing anything. So our circuit now only has those elements. So if our circuit only has those elements, so it comes straight to this point, nothing else, what are we looking at? The circuit is basically just the 10 kilo ohm resistor. And then here we have the capacitor. And then finally, we have the voltage source. So this is what we are looking at. Now, since this is for t less than 0, the V we get here as Vc is actually V for t less than 0. So it's V0. That's what we're getting. But here is a key point to remember. We'll keep using this as we move on throughout. When a capacitor is part of a steady state circuit, when in steady state, what is the behavior of a capacitor? A capacitor behaves like an open circuit. What if it was an inductor? An inductor behaves like a short circuit. So here what we have is a capacitor, and it's part of a steady state. There's a steady supply of electricity, so implying that this is a steady state circuit. It would not be steady if we had an AC supply, or if the uniform supply there was not there. Instead, you only had that capacitor. Then I would say it's not a steady state circuit. Currently, this is in steady state mode. So in steady state, the capacitor there opens up. So it will behave as an open circuit. V0 is the voltage across the points where the capacitor was. But since the capacitor is open, these lines are not connected anymore. It means that the 10 kilo is not using anything. What does that mean? It now means that the voltage difference between those 2 points will be equivalent to the voltage difference across that power supply. So V0 will be equal to 12 volts. So we get V0 as 12 volts. Once we know what V0 is, remember we wanted V0 to feed this, we need V0 and the time constant. So now let's get the time constant. For a capacitor, we did indicate that the time constant is RC. Now you have to understand that for this case, for this question, we're given, we have 3 intervals. We have our IT has to be seen for t less than 0, our V, not our I. We look at it for V, for t less than 0. For t less than 0, we have obtained V0 is equals to 12. Now we're going to look at for t greater than 0, but less than 1. Since the circuit changes once we exceed 1. So in this time period, what would be our VCT? And then the last part will now be an analysis for t greater than 1. And for t greater than 1, we are also going to come up with VCT. Now this will be the main one since it covers a wide range of time, but we'll have to combine it with this to get a full response. So let's look at t greater than 0, but within this range. So if we're dealing with that range, how will our circuit change? So in this case, now we are told to say that at t is equals to 0, the switch was changed and connected to point B. So what happens in that case? So when at position B, what do we see? At position B now, it means that there's no connection here. This is no longer there. Okay, someone joining us? So this is no longer there. In the same way, this is not there. No need for this. No need for this. But observe that even this part, the C line, is not there anymore. So this becomes the circuit that we are analyzing for t greater than 0, but less than 1. So this is what we are looking at. So we're looking at 0 less than t less than 1. So for that part, we want to get Vt, or the same Vc. We know it will be given by V0 E minus T tau. V0 is the voltage initially stored, and the voltage V0 is the one we figured out in the previous case, 12 volts. But we need to know the time constant. So what will be the time constant for a capacitor? It's RC. The capacitance here is 2 millifarads. So we have 2 by 10 to the minus 3. But what is the resistance? When you look at the circuit that we have, in this case, we only have one resistor, the 500 ohm resistor. So the total resistance in that circuit is 500. So when you multiply 500 with 2, we get 1,000. Then 1,000 by 10 to the minus 3, we get 1 as the time constant. Once we get the time constant, we can bring it here over 1, so that VCT will be equal to 4e to the minus t volts. But remember, this is for t in the range 0 to 1. It's not complete yet. We now move on to look at what happened for t greater than 1. So the problem says for t greater than 1, the switch is moved to position C. So since the switch goes to position C, what changes? Now this is moved to position C. If the switch is in position C, look at what we now have. Now this line is not there, meaning everything here is no longer useful. So this is not there. This is what we have now. What does it mean? So for this case now, we also want to find what VC is. So looking at t greater than 1, we know that VC t is equals to V0. V0 is the initial. At the point where we're starting from, what is the voltage? Notice that now the starting point is this value here. This is the voltage you'll be starting with at t is equals to 1. So our V0, our starting voltage, or we can even say V0, instead of saying V0, you can say V at the starting point, which is at t is equals to 1. And then E to the minus t over the time constant. When we were doing it for this one, our starting point was 0. That is why we got the voltage V at t is equals to 0. And the voltage at t is equals to 0 is the 12 volts from the first part. So when you're analyzing here, the starting value is what we got when we analyzed the previous one. The only thing we need to get is what will be the time constant for this change. The time constant, remember again, it's a capacitor, so capacitance times the resistance. Here again, we see that we only have one resistor, the 1 kilo, implying that the time constant will be RC. The resistance is 1 kilo, 1 by 10 to the power 3, multiplying the capacitance, which is 2 times 10 to the minus 3. The 10 to the minus 3 and 10 to the 3 will cancel, giving us 1 times 2, giving us 2 seconds. Now, we also want to account for V at t is equals to 1. We know the expression for it from the previous part. It was this 12 e to the minus t. So this is 12 e to the minus t. Now, you want to be very careful with what t represents. Notice that t counts time from t is equals to 0 going to infinity. But the use of t here, notice that we are restricting to only values of t which are greater than 1. What does this mean? This implies that our values of t should start from 1 going upwards. So what if we wanted to generalize so that this should now, it should consist of everything that we have here? What would we have to do? So if we wanted this to actually account for everything here, we need to make sure that when t is let's say 0, for t is equals to 0, for this expression, that shouldn't actually be a case. We should always start from t is equals to 1. We should start from t is equals to 1. What does that mean? It means that to the overall value of t, what are we going to do there? Can you guess what we're going to do? How are we going to present that t? I want to guess? Because we have to use a trick there. Okay. No one is confident. Okay, so since you want the count there to start from t is equals to 1, for this part, just for this part, want the count to start from t is equals to 1. So since we're starting from t is equals to 1, we want to use the general value for t. So since this we want for t is equals to 1 to be our starting point for the count, when you subtract 1 this side so that it initializes, you need to subtract on the other side as well, -1. So that now our initial starting point is going to be seen as t minus 1. So this is how we generalize it. So the expression that we're going to use here is going to be t minus 1. If let's say this expression was for t is greater than, let's say, 2, meaning would have our starting point to be t is equals to 2. This would imply that to initialize, this will have to be t minus 2 as the value for the time there. So in this case, what we use there will not just be t. Instead, we use the one where we have initialized it. And don't forget, the t minus 1 is in brackets. This is what is going to account for the values of t. And then this has to be over 2. So this is basically the t that we have there. It's like this second part had its own time frame, but now we want to generalize it with the value t that starts from when, or that more like matches what was happening here for the first part. Remember the first part here was different. So there we're going to have t minus 1. So this is e. The other part we haven't changed. This is still t minus 1 over 2. Be careful with the minus outside. It's negative for the whole expression for t there. Now, this one here, remember, this is the initial value. So the initial value for the second part, for this expression, occurs when t is equals to 1. So we're going to substitute t is equals to 1 so that we get exactly what value of voltage is going to be encountered immediately when the switch goes to C. So this is going to be 12 e to the minus. Since we are going for 1, it's going to be minus 1. Then e to the minus. This remains general because this is not just for 1. This is for any value of t greater than 1. Minus 1 over 2. So this becomes the general expression for our voltage VCT. You can evaluate what 12e to the minus 1 is, or you can leave it like this. So the question